Welcome. In high-performance AI computing, the physical layout of your network cables matters just as much as the switch bandwidth. Today, we will explore rail-optimized topology, the gold standard for connecting massive GPU clusters. To understand why we need a new topology, we must first look at the limitations of the old ones. In traditional data centers, leaf-and-spine architectures aggregate traffic from servers to the core. This works fine for web traffic, but AI clusters are thirsty for compute. They generate massive elephant flows that are far more bandwidth-intense than typical enterprise workloads. When thousands of GPUs attempt collective operations like all-reduce, flood the network simultaneously. In a standard topology, these flows often collide at the spine layer, causing uneven load distribution and congestion. This bottleneck slows down the entire training job, necessitating a rethinking of network design. This diagram illustrates a traditional leaf-spine architecture. Notice how traffic from node 1 and node 2 traverses through the leaf switches to the spine switches. In this mixed traffic scenario, highlighted by the red dashed lines, massive AI flows compete for the same uplinks. Because the traffic is aggregated without specific alignment to the GPU requirements, collisions occur at the spine level S1 and S2, limiting the total effective bandwidth available for the workload. Optimized topology solves the congestion problem by fundamentally restructuring the physical network. Instead of a messy web, we create parallel high-bandwidth data paths called rails. Ideally, we configure the system so that GPU 1 in server is paired with network card 1, which connects exclusively to leaf switch 1. GPU 2 pairs with network card 2 and connects to leaf switch 2, and so on. This creates a scenario where GPU 1 in one system is only ever one hop away from GPU 1 in any other system. By aligning the physical cabling with the logical requirements of the GPU, we create a non-blocking all-to-all fabric. Here we see the clean separation provided by rail-optimized topology. The top path, rail 1, connects GPU 1 from server A directly to GPU 1 in server B through a dedicated leaf switch. The bottom path, rail 2, does the exact same for the second GPUs. These parallel rails operate independently. Traffic from rail 1 never interferes with rail 2, effectively multiplying the bandwidth and eliminating the collisions we saw in the previous slide. Is this specific cabling so critical? It comes down to the math of deep learning. Training operations use a pattern called all-reduce, where every GPU needs to share results with every other GPU to update the model weights. In a rail-optimized design, because the network is aligned with the GPUs, these massive data exchanges happen without interference between different flows. This minimizes latency and ensures predictable performance. Furthermore, layout is essential for optimizing libraries like NVIDIA NCP-AIN, which orchestrate these transfers. By keeping the network simple and parallel, we allow the software to drive the hardware at maximum efficiency. This sequence diagram demonstrates the simultaneous, non-blocking nature of the traffic. On rail 1, GPU 1 from node A sends all reduced data to GPU 1 on node B via leaf switch 1. At the exact same time, on rail 2, the GPU 2s are exchanging their own data via leaf switch 2. Because they use physically separate switches and links, there is zero contention or waiting. This parallelism is what allows AI clusters to scale to thousands of GPUs. See this in the real world? We look at the NVIDIA DGX Super POD. A single scalable unit SU consists of 20 DGX systems, and the design relies on 8 separate compute fabrics, one for each of the 8 HCAs in a node. To scale this beyond a single unit, the architecture introduces spine groups and core groups. And at this massive scale, connecting 140 nodes or more, the rail-optimized principle holds true. Specific HCAs connect to specific leaf switches, which then fan out to spine switches in a structured fat tree topology. This ensures that the high-performance characteristics are maintained even as the cluster grows. This diagram visualizes the hierarchy of a super POD. At the bottom, a compute node has multiple HCAs. HCA 1 connects to leaf 1, representing rail 1, while HCA 8 connects to leaf 8, rail 8. These leafs connect up to their respective spine groups SG1 and SG8. Finally, everything is interconnected at the top by the core group. This structure ensures that the parallel rails we established at the server level are preserved all the way up the network hierarchy.